Now, before we get into Le Chatelier's principle, let's do a super quick recap on equilibrium. I've got a whole video on this where we go into detail, but just to make sure that you are all caught up, when a reversible reaction is at equilibrium or dynamic equilibrium, then the two conditions are the forward and reverse rates are equal, or the rates of the forward and reverse reactions of that reversible reaction are the same as each other, they are equal, and the concentrations of reactants and products remain constant. Now, this is the one that we're really going to be focusing on because it allows us to start to think about the position of equilibrium. Because, and this is so important, right? There's one thing you're going to take away from this intro. Just because the concentrations of reactants and products remain constant, so there's no net change, that does not mean, and I repeat, that does not mean that the concentrations of reactants and products are the same as each other, right? They're no longer changing, but there might be more reactants and products, there might be more products and reactants. It's just that those concentrations are no longer changing. Okay, again, head back to my previous video on chemical equilibria for how we look at that graphically. Now, based on whether or not we've got more reactants or more products at equilibrium, we can talk about that as the position of the equilibrium. So in our first example, if our purple circles are our reactants and our black ones are the products, then we can see in our first example, we've actually got equal concentrations of reactants and products at equilibrium. So we can say that the position of the equilibrium is just in the middle or in the center. Whereas if we go over to option number 2, where we can see that we've got more product particles or a greater concentration of products and reactants at equilibrium, then we say that the equilibrium or the position of the equilibrium is towards the right or the right-hand side. The reason that we say the right-hand side is because if we are to write just a general equation where for a reversible reaction or really any reaction, we've got our reactants in equilibrium with our products, the reactants are on the left of the equation, the left of the arrow, the products are on the right of the arrow. So if there are more products than reactants at equilibrium, then we say that the position of equilibrium is towards the products or on the right or on the right-hand side. And then if we look at our final option, we've got more reactant particles or a greater concentration of reactants than products at equilibrium, which will say that equilibrium lies towards the left, again, because reactants are on the left of the arrow and products are on the right. Okay. So, as I'm going to emphasize one more time, at equilibrium, the position of that equilibrium can be bang in the middle, it can be towards the products on the right, or it can be towards the reactants on the left. But let's say we don't want it to be on either of those sides. We can change the position of the equilibrium because the position will change in response to changing conditions. Those key conditions here being changing concentration, changing temperature, or changing pressure. And the way that the position of an equilibrium responds to changes in conditions is understood using Le Chatelier's principle, and that is going to be what we're going to now dive into properly. So Le Chatelier's principle essentially tells us that when a system is at dynamic equilibrium and a change is made to any of the conditions, then the system responds to counteract that change. Now, even though this is chemistry, I kind of like to think of this like homeostasis in biology because I think it just makes it a lot easier to grasp in the sense that if your blood glucose levels get too high, then the various systems will then move to bring that glucose level back to where it was before, right? Same with temperature. If your temperature gets too high, then your systems will move to bring that temperature back down to where it was before. And it's essentially the same with your equilibrium. If we change something, change a condition, then the system is going to respond to try to oppose or counteract whatever that change was to establish a new equilibrium. So, first example, and probably the simplest, is if we're looking at concentration. Okay, and again, all we're thinking of, whatever we do, the system is going to try to oppose that change. So here's a practice question. We've got chromate ions, which are yellow, and react with hydrogen ions in acid to form dichromate ions, which are orange. Sure, this is our equilibrium. This is our reaction. If some acid is added to the equilibrium mixture, will the mixture become more yellow or more orange? So let's consider what we're doing. We're adding some more acid into our system. So we are increasing the H plus concentration. Now, if we are increasing the H plus concentration, this is our change, then what's the system going to try to do? It's going to try to oppose that change. How does the system oppose the change? Well, it must do that by decreasing the H plus concentration, right? It's got to do whatever the opposite is. Now, how is the concentration of H plus going to decrease? Well, we're going to have to shift to the side of the reaction where there isn't any H plus, right? We're going to have to use that H plus up, which means we're going to have to shift the equilibrium to the right-hand side, which would use up any of those added H plus ions, giving us more of our dichromate ions. So how oppose change by decreasing the H plus concentration by the equilibrium shifting to the right-hand side or towards the products. Okay. Now that we've shifted the equilibrium to the right, which is decreasing the H plus concentration, that is where our dichromate ions are, which means if we are now increasing the concentration of our dichromate ions as a response to that increasing H plus concentration, then our solution, our mixture, is going to look more orange because we've got more of our orange ion. Right, let's go through those steps again. We increase the H plus concentration by adding acid. The equilibrium will shift to oppose that change. So we'll have to shift to the side where there's isn't H plus ions or aren't, using those up. And so we are going to produce more of our orange dichromate ions. Let's do another example, this time with temperature. Here we're given the contact process, so this is our equation, and we're told that the forward reaction is exothermic. Now, if the forward reaction is exothermic, that means that the reverse reaction must be endothermic. If the temperature is increased, state and explain what happens to the equilibrium yield of sulfur trioxide. So let's again think about this in terms of Le Chatelier's principle. What's the change and how will the system move to or respond to counteract that change? So the change is that we are increasing the temperature, right? That's our change. So then what will our response be? The system will try to oppose that increase in temperature by decreasing the temperature. Okay, now let's think about how temperature could be decreased. Well, if we think about exothermic and endothermic reactions, in exothermic reactions, energy is released to the surroundings, which means that our temperature of the surroundings increases, whereas for endothermic reactions, energy is absorbed or taken in from the surroundings, which means that the temperature decreases. So if we're trying to decrease the temperature, which direction will the equilibrium shift in? Well, the equilibrium is going to shift towards or favor the endothermic direction. And what is our endothermic direction? That is the reverse reaction, because we were told already forward reaction is exothermic, which means that the reverse reaction is endothermic. Now, if we are favoring the endothermic direction, so we're shifting in this way, that is away from the sulfur trioxide that we're trying to make. So what's going to happen to the equilibrium yield of sulfur trioxide? Well, that's going to decrease, unfortunately. Oh, can I spell? Is going to decrease because we're shifting towards the reactants, which is away from the SO3, as opposed to towards the products, which is towards the SO3. Okay, so far, hopefully so simple. Whatever the change is, let's oppose that change. Let's do one more example, this time with pressure. Now, when it comes to pressure, we are only dealing with gases. Right? We only care about gases if we are changing pressure as our condition. And what we need to consider is if there are more moles of gas in a given volume, then we are going to get a higher pressure. Okay, and then vice versa. Fewer moles of gas means a lower pressure. So let's see how we can apply that to an example. We've got, again, the contact process. We love this equation. Again, we're going to see it so many times over the course of your A-level studies. If the pressure is increased, what happens to the equilibrium yield of sulfur trioxide? Let's go through the process. Let's think about it step by step. The change is that we are increasing the pressure, right? That is the change to the system that's being made. So how are we going to oppose the change? Well, we're going to oppose the change by decreasing the pressure. How are we going to decrease the pressure? Well, the equilibrium is going to have to shift to the side of the reaction with fewer moles of gas. Because as established at the beginning, the more moles of gas there are, the higher the pressure. So the fewer moles of gas there are, the lower the pressure. So if we're trying to decrease the pressure, we're going to have to shift to the side with fewer moles of gas. Which side has got fewer moles of gas? Well, let's count. On the left-hand side, we've got 2 SO2s and an invisible 1 O2, so that's 3. On the right-hand side, we've just got 2 SO3s, so that's 2. So fewer moles of gas is on the right-hand side, or towards the products. And if we're shifting towards the products, then we're going to increase the equilibrium yield of SO3 because we're moving towards the side with fewer moles of gas, which is where the SO3 is. And that is essentially it. Make sure you can spot what is the change. How is the system going to respond to that change? So to oppose or to counteract whatever that change is. Which side is that? And then how does that affect whatever it is that they're asking you what it affects? If they're asking about the yield, which is how much of something you're making, then if you're going towards it, you're making more of it. If you're going away from it, you're making less of it, right? Keep that in mind. You're going to apply this again across so many topics. Make sure that you have liked this video, that you have commented if you've got any questions, and you subscribe so that you see any future videos on my channel for A-level chemistry.